As the world continues to grapple with the challenges of climate change and the urgent need to reduce greenhouse gas emissions, innovative technologies like carbon capture and storage, CCS, have gained prominence as a potential solution. CCS technologies aim to capture carbon dioxide, CO2, emissions from various sources, such as power plants and industrial facilities, and store them in geological formations underground. This process prevents a significant amount of CO2 from entering the atmosphere, thus contributing to global efforts to mitigate the effects of climate change. Components of CCS. Carbon capture and storage involves three main components: capture, transport, and storage. Capture. CO2 capture is the process of separating carbon dioxide from other gases produced during industrial processes, power generation, or even directly from the atmosphere. There are various methods of capture, including post-combustion capture, removing CO2 after fuel is burned, pre-combustion capture, removing CO2 from the fuel before combustion, and oxy-fuel combustion, burning fuels in oxygen-rich environments. These methods utilize solvents, membranes, or other technologies to capture the CO2. Transport. Once captured, the CO2 needs to be transported from the capture site to the storage site. This is often done through pipelines or other transportation methods, similar to those used for transporting natural gas or other fluids. Storage. The captured CO2 is stored in geological formations deep underground, such as depleted oil and gas reservoirs, saline aquifers, or unminable coal seams. The CO2 is stored in a supercritical state, which means it is in a dense fluid-like phase. Geological storage sites are chosen based on their capacity, security, and the potential for long-term containment. Types of CCS. There are two main types of CCS applications. Industrial CCS. This involves capturing CO2 emissions from industrial processes like cement production, steel manufacturing, and chemical production. These processes often emit a significant amount of CO2 and are challenging to decarbonize through other means. Power sector CCS. In this application, CO2 emissions are captured from power plants, particularly those that burn fossil fuels like coal, oil, and natural gas. While the transition to renewable energy sources is crucial, CCS can help mitigate emissions from existing fossil fuel power plants during the transition period. Benefits and challenges. Benefits. Emission reduction. CCS technologies can significantly reduce CO2 emissions from high-emission industries and power plants, which play a significant role in global emissions. Transition support. CCS provides a bridge towards a low-carbon future by enabling the continued use of existing fossil fuel infrastructure while reducing emissions. Negative emissions. CCS combined with bioenergy, BCCS, can result in negative emissions, where more CO2 is removed from the atmosphere than is emitted, aiding in efforts to reach carbon neutrality. Challenges. Cost. CCS technologies can be expensive to implement, particularly in terms of capture and storage infrastructure. Government support and carbon pricing mechanisms are often required to make CCS economically viable. Public perception. There can be public concerns regarding the safety and long-term storage of captured CO2 underground, as well as its potential impacts on local communities and ecosystems. Scale and infrastructure. Establishing the necessary infrastructure, including pipelines and storage sites, on a large scale can be technically challenging and time-consuming. Leakage. Ensuring the long-term integrity of storage sites is critical to prevent CO2 leakage, which could have environmental and safety implications. Current status and future prospects. As of my last update in September 2021, CCS technologies have shown promise in various pilot and commercial projects around the world. However, widespread adoption has been slow due to the challenges mentioned earlier. Governments, industries, and researchers continue to explore ways to improve the efficiency and cost-effectiveness of CCS technologies. In the future, CCS could play a significant role in achieving global emission reduction targets, especially in sectors that are difficult to decarbonize using other methods. Continued research and innovation are essential to overcome the technical and economic hurdles associated with CCS and make it a more integral part of the global strategy to combat climate change.